like that one. The force be with you. Use the force. Those are good. I'll give you guys about another minute. Well, it looks like a lot of you have been reading Chris Ferry's book. I know I got a lot of folks in here that either have nieces or nephews or little kids around the house. Chris Ferry writes a bunch of physics books for babies. Quantum physics for babies, ABCs of biology, ABCs of mathematics, ABCs of statistical physics, ABCs of Newtonian physics. It's pretty cool. They're actually pretty entertaining. So looks like you guys have got most, you at least have a familiarity with what force is. I'm not going to go into it just yet because I want to do the trivia question. And I want to trivia questions, and I don't want to give them away. So we've got that one. We can come back to that. So that's pretty good. So let's do some trivia questions. Let's play trivia. All right. So, in order to complete calculations Jade wants to make about her activities, she needs to know her mass. Exactly what property does her mass measure? And it's a fill in the blank. And I will warn you, my son plays trivia at various places, and his team usually does wickedly well. And they know stuff that I have no clue about. Okay, so I've got a couple of matters there. Matter stuff. But we're asking about its property. Okay, asking about its property. So the amount is important. Got some good thoughts in here. So we'll twist the thinking a little bit. If we're all on the same surface, do I have something else that I might worry about? Think about a running back versus an offensive or defensive lineman. Or a rugby scrum. I like that one. That's pretty cool. I like that one. Oh, come on, be brave. Nobody can tell who's answering something. Come on. Give you another minute here. But do you want to throw anything else up there? Okay. Well, so matter stuff, right? Matter stuff. And the question I have for you is, which is harder to move? A ton of bricks or a ton of feathers?
Are they on the same surface?
They're on the same surface. They both weigh a ton. So which one's harder to move? And if I assume frictionless, because there is the possibility that the force due to friction between the brick and the surface is different than the feathers in the surface. So if I have a frictionless surface, which one of those things is harder to move? Why?
What did you say friction is?
Frictionless, if it's frictionless. Yeah. No, it's a disregard friction. It's going to be the same. Okay? Because they both have the same mass. So density, now my ton of bricks is going to be in a lot smaller spot than my ton of feathers. So the density is not going to come into play, at least in terms of the property of mass. Now, the fact that I would have my ton of feathers, depending on how I've dealt with my ton of feathers, you know, if I've compressed it and put it in a bag and it's the same size or volume as my ton of bricks, then I'm going to have a difference in pressure because of how it's spread apart. So when we get to pressure, you're going to see that. But so density's got some effect, but it's not the effect that we're looking for in here. I've got the pull of gravity. Well, the pull of gravity is an effect of the mass, but what we're looking at is the start, how I'm going to have to deal with something is what we call inertia. So the property of mass, if something has more mass to it, it's got more inertia. It's going to make it harder to change its motion, right? It's going to make it harder to change its motion. So I do like the answer of resistance of acceleration because that's actually the definition of inertia. Okay? It's the resistance to getting it moving. So they've got inertial up there and a resistance of acceleration. So if I were the judge in the trivia contest, I would say those two answers were the correct answers. But there's a lot of stuff in there. Now, friction comes from that inertial part, and we'll talk about it. Friction is a result of some of this stuff. So that's where we are on there. So, all right, so that's that trivia question. Okay, so let's go to the next one. All right, so the question is, we all know the Earth is locked into orbit around the sun thanks to gravity. But exactly how far does the force due to gravity go? I like it. I like it.
At least.
everybody hear about the airplane in India last week? Or I guess it was Wednesday. Pilot forgot to pressurize the cabin on the way up. Oh, yeah, it was bad. I have flown in an unpressurized aircraft. It ain't fun. And I flew over parts of the Andes. It ain't fun. Okay, everywhere's good, but let's think of it in terms of a distance.
Do you want the sun's gravity or gravity itself?
Gravity itself. Well, you can even think of it as the sun, if you want to think of it in terms of how to answer it. Pluto got demoted. Actually, we have now found about 50 objects in the asteroid belt that actually have more mass than Pluto. The poor guy who demoted Pluto got hate mail. The poor astronomer who actually did it, they're actually pushed to get Pluto demoted, has had death threats. Hearing interviews with the guy is pretty fun. It's noticeable after Pluto. I like it. Somebody got on Google? I like that one. We'll stop with that one. It is to infinity and beyond. It is it actually, even beyond Pluto, we still experience it. The two Voyager 1 and Voyager 2, which have actually gone past one of them has actually gone is what we consider escaped from the solar system, but our solar system is influenced by the other stars in our galaxy, and our galaxy is influenced by other galaxies, and so gravity definitely drops as 1 over r squared. Okay, so as I move away from the sun, or as I move away from something else, it's going to drop as 1 over r squared. As a rule of thumb, when you guys take something like the MCAT or take an entrance exam, when in doubt, have the force drop as r squared, 1 over r squared. When in doubt, because that actually works out on a lot of different things that we play with. That behavior is dropping as things go out of distance. It'll either go out as 1 over r, or it'll go out as 1 over r squared. And you're going to see that over and over and over again. So to infinity and beyond is a really good answer. All right. So I know it's early and it's a Friday, but I thought this would be fun. So we got one like this. So I've got some multiple choice. Okay, got multiple choice here. Okay, this one is I'm pushing on a boulder, but it won't budge. It must be magically glued to the ground. But it's not magic, it's physics. Yeah, it's good old physics. Which of these laws makes the most sense for the rock not moving? So A is conservation laws, B is motion laws, C is thermodynamic laws, and D is Hooke's law. Got weird numbers in. I like that. It's more fun to have weird numbers. Anybody else want to chime in? Looks like some of you did your pre-work. Newton's laws of motion. And we'll find out about Hooke here as well. It's Newton's laws of motion. All right. Another one. Get you thinking. Get you applying stuff that you already know, like this one. What is the SI unit of weight? And I've got A is kilograms, B is pounds, C is ounces, and D is newtons. Anybody else want to chime in? This one kind of is a problem because we typically will say things in our weight in kilograms that is not actually correct. Kilogram is a mass, and even though we use in our common vernacular kilograms, it's not a weight, it's actually a mass, and the weight is actually newtons. Our SI unit of weight is newtons. Alrighty. So when you're on your trivia question there, you'll know the difference. All right. This one. Newton was a famous English physicist. Actually, he wasn't a physicist. He was a natural philosopher. Came up with three extremely important laws. They are known as the laws of what? Fill in the blank. Good. Oh, I like that one, motion. That's good. Looks like you guys got it. Okay, it's motion. Newton, interestingly enough, a bunch of them at the time were all natural philosophers. We actually didn't call somebody a physicist until about 1910, 1908. In fact, my physics books from around 1900 are all textbooks in natural philosophy. Is what they're all textbooks in natural philosophy. They are not textbooks in physics. So, and actually a lot of people would say that Newton was more of a mathematician than he was a physicist, but he was also very much a natural scientist. corresponded with a lot of other natural scientists at the time, which is very interesting because you can actually look at stuff. I will probably put out for a link for you guys starting next week. All of Newton's laboratory notebooks, all of his journals, all of his handwriting, all of his handwritten stuff is actually, all of his notes for Principia Mathematica are all out and digitized by the Cambridge Library. You can actually go and look at them. It's really nice because his handwriting is very legible, provided that you can read cursive. He's written it very out. It's interesting because at the time we didn't have standardized spellings. So he actually spells things differently throughout his journals. But you can actually go back and see his calculations, see his handwritten calculations. Some of the journals are in better shape than others, but they're all digitized and they're all translated. So you can go back. All right, so let's look at the next one. All right, so we've got gravity. What's the name for an object that has so much gravitational force it is believed too great to allow anything to escape, even light? I like it. Oh, it's good. Oh, it's good. Hey, at least people are having fun, right? That's good too. Looks like most of you got it. It's a black hole. It's very, very dense. And we believe that that's what's happening there. Alrighty. Okay. Now we're going to get a little more technical. If you apply twice the force on an object for twice the time, there will be a change in velocity will be 2 times greater, 4 times greater, no increase, or 8 times greater. All right, it's 4 times greater, and we will talk about how we get to 4 times greater. But the easy way from a solve the problem test taking 101 type of a matter is I've got twice the force, twice the time. 4 is probably a logical choice. 2 times 2 is 4. That's a good test taking method in order to get something to resolve. Used to drive my mother crazy. She was a nursing student and she was practicing for her nursing exams. and you'd hear them read the question and hear them read the answer. I said, well, it's going to be either A or C. And she said, but you haven't even had that material. You don't even know what the material is. I said, yeah, but listen to the way the questions are read. And so you can narrow it down to 50-50 and then be able to work it out. So there's a lot of good test-taking skills that are out there. And this one, the easy way to do it is 2 times 2. Logical answer might be 4. Or, 2 cubed, which gets you 8, but that's not a usual thing that we have happen. So that one's that one. But we will get to explaining why that one is 4 shortly. All right. So we have an object at rest on a flat surface. Gravity is always pushing down. The normal force is always pushing up. Which force is greater? A is the gravitational force pulling down, B is the normal force pushing up, C is that they're equal, and D is the force due to friction. Anyone else want to chime in? You're right, it's the same. Unless my table is not big enough or not sturdy enough for the heaviness of the object. So then you usually see a bow in the table, but if I'm on the ground, it's going to be the same. All right, I think I've got one more. Yep. All right, which scientist made the discoveries in this field is following a law that's named after? The extension x of an object is proportional to the load. I didn't hear any chuckles. Dadgummit.
There was one.
Oh, and I didn't, because you guys had a test on Wednesday. I didn't tell you the fun fact. How many people are fans of The Simpsons? Good old Simpsons. Yeah, I got some. Got fans of The Simpsons. Apparently, the writers for The Simpsons, one of them is an MIT graduate. 2 of them are mathematicians. One of them is a physicist. And apparently, there are lots of hidden mathematics clues and cues and all kinds of stuff in The Simpsons, to the fact that when they first put there was a theorem that they had presented in The Simpsons that hadn't been solved, and somebody just recently won the prize for solving the problem, but it was actually highlighted in The Simpsons. I didn't know. I had no clue.
There was a question about how The Simpsons had pi, since all the characters only have 4 fingers.
Yeah.
Because the only person in the show with 5 fingers is their physicist.
Well, the only one they actually show is God.
Yeah.
Yeah. Yeah, because the question was presented: why don't the Simpsons count in base 8 instead of base 10? odd fun facts, right? Fun facts. Looks like you guys got it. Now, does anybody know what Hooke is most famous for besides Hooke's Law? Actually, most people don't know him for Hooke's Law, unless you play in the physics world. Huh? Hooke.
Pirate?
No, wrong pirate. I like it, pirate, not Captain Hook. Now, most of you, because in general physics, most of you are biology types, you actually know Hooke from something else. Yeah, he does springs. And he actually does springs because of his biology bent. Newton and Galileo looked at the stars. Hooke actually went microscopic. And one of his things that he's best known for is his drawings of the flea. And the Hooke's laws of the flea and dealing with the microscopes and going into the optics along those lines. And then he does a lot more biology. And his spring stuff, which is what we end up dealing with Hooke's law, is associated with trying to understand why a flea will jump. And one of the other things that he also did was looking at the electricity on the frog's leg and showing that the muscle movement was twitching. So he was one of those that did that. I'm not sure if he's actually attached to the frog's leg part, but he also talks about and does those kinds of experiments. Hooke was a contemporary of Newton, and they actually talked back and forth because Hooke also looked at light, and Newton does a lot of stuff with light. Even though we deal with Newton more so for his motion laws, there's an awful lot of optics that Newton did as well. And then Hooke also did a lot of those optics. So it's kind of fun. So hopefully you guys now know that you know a heck of a lot about motion without me having to do anything. You already have it in your bailiwick. So that makes it a little easier to say, okay, don't make this harder than it is, right? Don't make this harder than it is. You guys have been playing with this for a long time. So we can get into the technical definitions, right? We can get into the technical definitions of this stuff that we already know. If I do something simple, we say a force is a push or a pull. That's kind of the fundamental simple part. So if I'm getting Chris Ferry's book out and General Physics for Babies, they're going to tell me a force is a push or a pull. And that's pretty much where it is. But we have a lot of things that comes out. If we want a technical definition, and I will give you Newton's definition as we go along, and we're going to see a couple of things as we go along as well. But typically what we get is that the definition is an influence on a body, and that just means an object. You've got some sort of object out there or system producing or tending to produce a change in movement or in shape. So we've got something that's going to create a change in movement or a change in shape. And that's probably the more universal definition of a force. And so if we think of a good old balloon here, if I've got a balloon that looks more like a mushroom. Let's see if I can draw a better balloon. It is Friday, right? So I've got a balloon on a string. And if I apply a force to this balloon, and I'm applying a stationary force to the balloon, I'm going to deform the shape of the balloon. I may or may not get a change in motion. But if we're talking about things like hockey pucks, And we use hockey pucks. One of the reasons we use a hockey puck is because it's probably nearly frictionless. I've got a frozen hockey puck on ice, and it's probably nearly frictionless. And so we use hockey pucks a lot. But if I apply a force on my hockey puck, I am likely to get that hockey puck to move off. Right? I'm likely to get that hockey puck to actually go somewhere. If I have that hockey puck moving and it hits the boards, it's going to have a change in motion. Okay, it's going to have a change in motion. So we know that we end up with these changes in motion that are out there. There are two types of forces that we deal with. This one right here, where I've applied the force to the hockey puck, is what we call a contact force. I've actually applied a push or a pull directly. I've done something to actually transmit some energy to the hockey puck to have it go. And that results from contact. So kicking a ball, hitting a ball with a baseball bat, hitting a ball with a softball bat, striking a basketball to or have it go through the basketball hoop. My running back running into the defensive lineman. All of those things are going to come into what we call contact forces. Now, we also know we have a second type, and we call it a field type. That's a field force, that we have something that's causing motion that is not necessarily directly in contact. And one of the best descriptors of that, besides gravity, but we can actually play with it a little bit, is if I have a north and south magnet, and as I bring these closer together, what's going to happen? They're going to come in and they're going to attach. If I have two north poles, which is also always kind of fun, because I can move this north pole around, I can actually push that magnet away without actually physically coming into contact with the magnet. And so we get what we call fields. And my field forces, so if I have a positive charge and I bring another positive charge in there, they're going to repel each other. And I can actually draw these field lines around my charges so that I can actually demonstrate an electric field. So I can have an electric field, I can have a magnetic field, and I can have, here's the sun, I can have a gravitational field as well. So I can actually, so we have, gravity is what we call a field force. And we go back and look at those field forces. So one of the things that we know, because we've been watching it, is if I have that lovely hockey puck and I send it off, what's that hockey puck going to do? I'm not having another hockey player right now, but if I send that hockey puck off, what happens? It's going to keep on going until what happens? So it strikes something, because it's pretty well nearly frictionless. We know that if I do that in space and I have a wrench that's flying across the space shuttle, it's not going to stop. It's going to stay and it's going to head that direction until something stops it, something else gets it. And that gets us Newton's first law. And Newton's first law is that an object, and I'm not going to spell out, well, I am going to spell it out, moves with a velocity that is constant in, constant in magnitude and direction unless a non-zero net force acts on it. Right today. Or simply put, an object in motion remains in motion, an object at rest remains in rest unless it's acted upon by another force. Don't have to get so complicated, okay? That's what our book's going to tell us, but essentially it is, as long as there's not another force acting on it, it's not going to change direction. It's going to sit on the table. As long as I don't do a push or a shove or move the table out from underneath it, it's going to sit there all day long. An object in motion remains in motion. An object at rest remains at rest unless acted upon by another force. And we say net zero force because we all know what happens. If I have a person pushing on another person, I can increase the force, but the other person can resist that force just as greatly, and nothing's going to happen. If I've got two things pushing on each other, nothing's going to happen. And I have to have a net force greater than zero unless for something to happen. So, when we talk about that inertia piece, I have a refrigerator here. Okay, I got my little refrigerator, and the more massive the refrigerator, the more force I'm going to have to apply in order to get that refrigerator to move. Now we know we've got things that are acting on us besides just surely the mass of the refrigerator. But if I have the refrigerator on a frictionless surface, if I don't apply enough force, I'm not going to get that refrigerator to move. I'm going to have to apply a certain amount of force due to the mass of that refrigerator. Okay, due to the mass of that refrigerator. And that's what we call that inertial property. That the mass, I've got to have enough force to get that mass, and the bigger the mass is, the more force I have to apply in order to get there. So it's a direct relationship to that piece. So we can have that force. So we know we have to deal with it. So what we end up doing, and what you're going to end up doing a lot during the next, we're going to start doing this a lot, and I'm going to tell you the easiest way to do physics problems is to draw your picture. Okay? You draw your picture. What we end up with is, here's my refrigerator again. There's my refrigerator. We know it has a certain mass M. It's a big mass, right? And we know we have a force due to gravity pulling down on it. Okay? We know we've got that. It's a force due to gravity pulling down on it. We talked about a normal force because you guys already know what that normal force is. You just don't necessarily think about it. We have a normal force. And if I'm on a regular surface, I've got a force due to friction. And so what we end up doing when we start working physics problems is we write out what we call force diagrams, or we call them free body diagrams, just depending on how you want to deal with it. Because one of the things that we know happens to us is I can play with the center of mass. And the force due to gravity is going to act through what we call the center of mass. And we know this, and we've dealt with this, and we've played with it. And I'm going to see if I can do a demonstration in here. See if I can get the camera. Let's see if I can get the teacher camera. Okay, you guys see me over in Tonkawa? Okay. And we'll play with this because I have a good demonstration that I play with. But over here, I've got, this is a Mosby's Dictionary of Nursing Terms, okay? This is a Mosby's Dictionary of Nursing Terms. Now, we've all done this. We've all played with it. We all know about it. And I know that if I put my hand in just the right spot, I can balance the book, right? So the book here has a force due to gravity applying on it. It's coming down, and I'm applying a force to hold the book up, and I'm balancing it. If I'm really, really good, let's see if I can do it. I can ultimately get to, this book is particularly heavy, so Well, I'm not going to be able to balance it on these things smaller than the top of my fist, but that's still like only an inch out there. But intuitively we know, making the assumption that this book is a uniform book. Remember the physicist's definition of a cow is a sphere with the milk evenly distributed throughout. Because we like uniform things to work with, because we like to be able to pick where the center of gravity is. And that, of course, is not true, because we know that the milk isn't necessarily uniformly distributed throughout the cow. But I can treat this particular book as a uniform object. And we know intuitively where you have to put our hand in order to balance it out. Because if I put my hand over here, the center of gravity is going to have the book turn over. If I put it where we know intuitively that center of mass is, I can balance the book. Because it's uniform, I know it's about halfway between here and here. I know it's about halfway on this side. And if I really wanted to balance it, I know it's about halfway up in the book. But as long as my hand is directly underneath the center of mass of the book, it's going to stay balanced. So all my objects, and when we do a free body diagram, we're treating our object as if it's just at the center of mass, and all the mass is at the center of mass. So that big rock that you get, that looks like it can't possibly be balanced. If you go to Monument Valley and play with Wile E. Coyote, and we've all seen it, right? There's some big rock, and we got a big fat end, and it's a little lighter end over here. And this rock just doesn't look like there's any way possible that it could be balanced. Turns out that the center of mass of that rock has got to be over the top of that particular structure. Now, I do a demonstration if I'm in my physics lab over in Tonkawa, that I can take a physics book, and I have the table, and I can stack the physics book, and I can stack the physics book again, that I can ultimately get at least one book in my stack of physics books that's totally not over the edge of the table. This is how Frank Lloyd Wright was able to build some of his structures. He's all about where you can put the center of mass in order to make sure that it's supported, but it doesn't look supported. Because we can actually use the center of mass, and we'll actually, in a couple of chapters, we'll actually calculate where those center of masses are. But we've intuitively been doing this since we were little kids. I mean, how many of you have balanced the butter knife at the dinner table? Particularly when you're bored and you don't want to listen to what your parents have to say, right? We've all done it. Spoons, right? Spoons. Then it gets really and if you're at the cafeteria and you're listening to everybody, you've got the spoon balanced on the edge of the cup, and you got other things balanced all the way up. It's a big game of Jenga. That's exactly what we've got, is a big game of Jenga that we're having there. But ultimately, that's where my mass is going to act. So when we draw our diagrams, a lot of times we're just going to draw a dot. And we're going to have our force due to gravity, and we're going to have our normal force. I'm going to just write it out that this is my force due to gravity. And here's my normal force. And we call it a normal force because it's perpendicular to the surface that we're dealing with. We call it a normal force because it's perpendicular to the surface that we're dealing with. Because here is, and physicists love to do this, we love inclined planes. We love to play with inclined planes. So if I have an object on an inclined plane, I've got my force due to gravity. My force due to gravity is always pointing towards the center of the Earth. But my normal force in this case is going to be perpendicular to my plane, as it's going to be at a right angle. Okay? It's going to be at a right angle. I still am going to have balanced forces, because in this case, if it's sitting on the inclined plane, I've got a force due to force due to friction that's helping to hold me up, but I'm going to get my balance of forces. So drawing your pictures is going to really, really help you out. It's going to keep you from doing certain things. And my force due to friction, we'll get here in just a little bit as this we'll talk about what the force due to friction is. So we have Newton's first law. First law is the object in motion law. Then we got the famous second law. All right? The second law. And it relates to, so we're going to play tug of war here. I've got my little flag. I've got my other person on this side. And this is going to apply a force, and this is going to apply a force. If they are applying a force, now notice that I've drawn the force with an arrow. Forces are vectors. They're going to have direction and magnitude. Forces are vectors. They've got direction and magnitude. So, if my two people are applying an equal force, what happens to the flag? Flag's going to stay put, right? Flag's going to stay put. Now, if this person applies twice the force of the other person, how's the flag going to move? Well, we'll move this way, right? Yep, it moves that way. Now, if this person applies 3 times the force, because the other person is going to react to it, now we're going to get the flag to go that way. Okay? Basically, the motion of the flag is going to be the result of what we call the net force. So I'm going to be able to add these forces, so I'm going to use a big sum, right? I'm going to use a big sum of my forces, and the sum of my forces is going to give me my net force. So if I do this sum of the forces here, I now have a negative 3 forces plus 2 forces is going to give me a negative force, and that negative gives me the direction that it's moving over there. Which is one of the reasons why I spend so much time early on about how we're going to play with forces, because we are going to play with forces in 1 direction, 2 directions. We probably won't get to 3 dimensions, but we actually get forces in these directions all the time. And we use this all the time. For example, if I have a nice little lamp here, I've got this nice little lamp, I've got the force that's being applied due to gravity, and I have tension in the rope. But not all the time do we have a just nice straight line type thing. I might have a sign hanging from 2 wires. And I can calculate the tensions in each one of those wires based on the forces. So all that vector stuff that we've been doing, we are going to end up using again. We're going to end up playing with those vectors, which is why we draw our picture, because we want to know the places that we've got in terms of our motion. We want to know how that's going to work. Now, the net force, this is where Newton's law, second law, comes in. This is the general form that we use most often. All right? Because I'm going to tell you we lie to you. Right? I'm going to tell you we lie to you over and over again. But this one is my sum of my forces is mass times my acceleration. And this is what we commonly refer to as Newton's second law. That's not really Newton's second law. We lie to you. But that's the one that we're going to be using over and over and over again. Now, one of the trivia questions talked about if I apply twice the force at twice the time, how is that going to change its velocity? That's actually more how Newton defined the second law than this. This is just something that we commonly use, and we use it most often in this form. So let's go back and let's look at something along that line. So we know, because we've been doing kinematics and we drove you all crazy about it, we know that my acceleration is my change in velocity with respect to a change in time. That's my acceleration. That's the definition of my average acceleration. Newton said, for the second law, he said that if I apply an impulse, I'm going to get a change in what we call momentum. If I apply an impulse, I'm going to get a change in momentum. So if I have that hockey puck and I hit the boards, as soon as the hockey puck hits, it bounces back off. It had a change in momentum. And momentum is defined as mass times velocity. Okay? Momentum is defined as mass times velocity. And so we're looking at that, and I'm going, if that's what Newton actually said, that if I apply an impulse, I'm applying a force over time. So we apply impulses all the time. We've got softball players in here. Having my softball bat hit the softball is a change in momentum, and that's certainly an impulse. And if I apply the force on the ball, if I apply it really fast, I'm going to get the ball to do one thing. If I apply it slow, I'm going to get the ball to do another thing. If I play soccer, how fast I apply that kick, I can dribble with some light touches, or I can keep my foot on the ball a little longer, and it's going to change how things are happening. The impulse is really important. And impulse is actually defined as force applied over a specific time. Okay? So my force is applied over a specific time. So now if I have an impulse, I can rewrite this as a change in mass over a change in momentum, or a change in momentum. So now let's look at how I can rearrange this. Most of the time, like 90% of the time, if I have a baseball and I apply a force to it, the mass of the baseball doesn't change, right? The mass of the baseball is not going to change. So most of the time I don't have a changing mass, and so I can take that and I only worry about the change in velocity. So the trivia question, we said I have 2 times the force and I have 2 times the change in time. That's going to be 4. I have my force times change in time. I'm going to have a corresponding change in velocity, so it's going to be a factor of 4, is where that came from. So now let's go back here and let's look let's look at this. So if I still have this mass times my change in time, and if I play with this, I'm going to say, okay, I'm going to put my change in time on top over here. I got a change in velocity over change in time. Guess what that is? That's acceleration. And so my force, my net force, is going to be in the same direction as my acceleration. So because this is a vector quantity, mass is not a vector quantity, but acceleration is a vector quantity. But let's look at this a little bit more. We won't do too much on it, but I want to show you, here's your rocket science. Okay? So now y'all will be rocket science after this, right? Rocket scientists. When we say it ain't rocket science actually is pretty simple. So I've got my change. Typically what happens is we can rewrite this as a factor that's got my change in mass times my velocity plus my mass times my change in velocity. Most of the time, I don't have to worry about a change in mass. So this term just goes away. Most of the time, I don't have to worry about a change in mass. But if you've ever seen the shuttle take off, I've got one tank, I got a big tank, I have another little tank, and there's my little shuttle. I worry about a change in mass. Okay? I worry about a change in mass. Because I've got a lot of mass that's being consumed and I have to worry about it. So most of the time we don't have to worry about it, but in rocket problems we do. In fact, even for a little bit, we don't necessarily worry about it too much when we're driving our cars, but we actually have a change in mass in our cars. when we burn and consume the fuel, we actually slightly change the mass. It's just not enough to do a whole lot. So we can usually disregard that change in mass part. So we've already written Newton's second law in two different ways, but the one that we're going to use most for this, just for problems in this chapter, is that my net force is equal to mass times my acceleration, and my force is going to be applied in the same direction as my acceleration. Okay, we're going to define the third one, and then we're going to quit for the day because brains are full. Third one is easy. Forces come in pairs. Forces come in pairs. That's why I can draw on my refrigerator. I have a normal force and I have a force due to gravity. My forces come in pairs. If I'm applying a force this way, there's something that's applying a force back that way. The table is applying a force. Forces come in pairs. So, we will start there on Wednesday.